Okay, people, welcome back. I got pretty good response on my last video, and I said, like, even if nobody watches it, this is just a content for my AI overlords. So, what we're going to do today is we're going to start off where we left off, which was we're trying to implement a better tree search algorithm, much better than what Minimax is, and possibly make it a little bit more optimized. I'm not very optimistic towards it because I'm pretty bad coder. So, let's go. So we're going to do a 90-minute flow. I hope this is a long stream because I would really like to. I really like the long form content. A lot of people actually ask me that why do I make it? Why did I make it so long? And the answer is simple. If I really try to bring it down to a particular value, let's just say I say that I want to make it 15 minutes, and I really need to start trimming things out, and the amount of effort that is required to actually trim these things down, make it just make it look better and etc. It's not worth the time. It's just better that just share what I'm doing, man. Okay, so let's go. Okay. So what I've done till now is that I've actually I added this code for the node and etc. What we added the prior as well as the better the better prior to these things. There was a little bit of bug that I fixed. I'll just show it to you. So you can see it's now correct. It takes what was the last probability, the stupid mistake that I was doing. I figured it out after like 2 minutes after the stream ended, which was that I was sending this all the probabilities, but I actually needed to send only probabilities for that particular child. And so I've done that. It has generated this. You can see it has 195 nodes now. You don't actually need all of them, and all the 195 actually comes down to 17. And you can also add your own counter, and then also update this kind of thing, and you can see it returns. It has how many times that this particular thing occurs. Now, just a minute. Yeah. So I was going over the mu0 paper, and there's like a couple of differences with AlphaGo, which is that AlphaGo was a much simpler search algorithm. So AlphaGo used a search like this, as mentioned here. Each node was basically storing all these values, and the way the bonus was decided was using this particular formula, which was the bonus. It's basically an upper confidence bound kind of thing. It's a variant of PUCT algorithm. What is it? Upper confidence trees, lessons from alpha 0, multi-arm bandit. I don't know. Standard MCTS uses a variant of the upper bound confidence mixin formula called UCT, UCB for trees. Okay. Alpha 0 uses a version called polynomial upper confidence trees. If we add the state S and considering action A, we need 3 values to calculate PUCT SA, which is what is the mean action value, the prior probability as fetched from network, and the number of visit counts. So this is something. Okay, so this is exactly like what it's used here. So you can see that the upper confidence for any given state S is some constant times the probability that this action was taken in state S, multiplied by the number of actions, multiplied by the root of total number of actions that is in this state, divided by the number of 1 plus the number of times that this state was visited from this particular action. Where CUPT is a constant determining level of is the constant. Oh, just a minute. Let me close my window. where CPUCT is the constant determining the level of exploration. This search control strategy initially prefers actions with a high prior probability and low visit count, but asymptotically prefers actions with high action value. Okay. So in this thing, they basically describe the three parts that are in this algorithm, which is selection, expansion, evaluation, and backup. It's like a 4-part thing. And this algorithm was actually improved in the mu0 paper, which you can see here. In this appendix, I give what the search algorithm is. If you're lucky enough, or if I'm good enough, I'll be able to implement this. What this search algorithm does is zoom it for all of you. Okay. Each simulation starts from an internal root node S0, which is like this, that I'm in this particular given state, let this be my S0 or S0, and finishes when the simulation reaches the leaf node SL, which in this case would be, let's just say, this particular the simulation stops when it reaches here. Let's just say this is SL. For each hypothetical time step k is equal to 1 to L of the simulation, and an action AK is selected according to the stored statistics of internal state sk-1 by maximizing over the upper confidence bound. It's, as you can see, this is basically an improved version of this. So you have the QSA, and then you have this entire bonus piece, which is the probability, blah 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 blah. This part is same, while the constant CPUCT is actually expanded or broken down into two different constants. So you have this entire piece. Then you have the expansion, which is this piece. How do I actually expand at each time step k? At the final step L of the simulation, the reward and state are computed by the dynamics function. This is. I don't need that because this is not a mu0 algorithm. We don't actually store the dynamics. Storing the corresponding tables, blah blah blah. The policy again. They also generate the what is this state and the reward, because it's a mu0 algorithm. In this algorithm, they actually learn the dynamics, whereas we don't actually need this kind of thing. The policy and value are computed by the prediction function. This makes sense. A new node corresponding to the state SL is added to the search tree. Each edge SLA from the new expanded node is initialized like this. So you can see the n actually starts out when the node is actually initialized. The number is actually 0, where in our case we actually add this number to 1. Oh, wait, I haven't actually ported it. Yeah. So and we have included n is equal to 1 because each time it initializes, we assume that the model has actually come here, but it should be 0. Note that the search algorithm takes at most one call to the dynamics function and prediction function respectively per simulation. The computational cost is of the same order as in the AlphaZero. Okay. Then you have the backup. People, you should know your backups. If you don't know your backups, you're in deep trouble. But you have a backup function, this thing, and it's like a standard backup function. Then so again, GK is actually the state backup. The question is now, how do you convert the state backup, which is GK, to actually action value, and this is the form that they use. And you basically these are the update rules for that particular thing. In two-player zero-sum games, the value function are assumed to be bounded within the 0-1 interval. This choice allows us to combine value estimates with the probability using the PUCT rule. Equation 2, this thing. However, since many environments the value is unbounded, it is necessary to adjust PUCT rule. Okay, so this is just a normalization method. So this is a simple min-max normalization. It's pretty smart. Okay. Now the next thing, so this is what we are going to try to implement today. The next thing that we have is that unlike all these algorithms which get the perfect representation of the board as an input, this board that these are the pieces here, and these are the so these are all these units that are on this board, and these are the exact locations of where they are on the board. We don't have that in our case. What the way algorithm works is that you have you have the first flag, which is game. It basically means that the game has just started, because it's equivalent of the BOS tag in neural language models. Game, you have the move 1, you have the move 2, you have the move 3, move 4, move 5, move 6, 7, 8. Okay, cool. And so at each move, so now what's happening is we are still going to say that W is the player that's going to play here. This is W, this is black, this is W, this is black. Okay, black, W, black. Okay, cool. So right now the model, so this is for our reference at this point of time. What the model knows is that these are all the moves that have been made till now, right? So this is our state. Our state is actually a set of all the moves that have been taken till now. So A0 all the way to A8. This is the state. Now what the policy does is that policy network is basically pi. It takes a look at the state and takes what is it, it gives us the distribution against that particular state. Now what this does is all it's going to do is that going to take this information. Right, this is a policy. It takes all the actions that have been taken till now and predicts what should be the best action. So you can consider this as A9, and this would be policy at 9. E9. Oh, god damn it. Now the other thing to note is that your value function in general methods, so you have something called VS. This is your state value function. In our case, what you can see is that the value function is also going to take in these values. Okay, so now my question is, in this kind of a situation, how do we distinguish between what is an action value and what is a state value? The way model works right now is that it's a transformer model. So it takes what is the whatever are the moves that have been taken, it feeds it to model. It's a simple GPT-2 model, and it predicts two things. One is the what's the probability of moves, probability of legal moves, and the second thing it does is it predicts the value, which is who wins, which tells us who actually wins. So combined with, so these are the two things that the model predicts. Now my question is, how different are the value function as well as the state value function and the action value function, which is Q S comma A. So in this case I have Q S comma A, which should eventually become okay. Does this make sense? What is the conventional backup formula? So the conventional backup formula you have is that QS of A can be given by sum over all the future states as well. So everybody needs to know the backup diagrams, man. Know your backup diagram. Right. I'm not going to give a lecture on RL, but this is your backup diagram. What this means is that you have a given state S, there's a probability distribution with which you can take different action, which is given by the pie or policy, and you take some action A, and then this is one level. And then if you go to the further step, which is with action A, if you take an action A with the dynamics function P, which in our case is completely deterministic, but in real world scenario it might be probabilistic. With the dynamic function P, it's going to go into any future state S, leading to a reward R. And so you get these two equations, which is using which you can give out what are the probabilities, what is the actual Q value state and the value state. Now in our case, this is a completely deterministic function, and the value is going to be 1 again. Okay. Let's just assume I'm right now. So the way you would go about it is, okay, so I have these nodes. I have self.p, which I'm actually not capturing weirdly, and because all these nodes, they also so in this case we only need the first 3 values. We don't need what was the reward and the actual state embedding here. So because you need 3 values, which is npq, we have np and we have q is equal to 0 for simplicity, because we're going to keep adding to this thing. And so q is the action value for being in state S and taking action A. Okay, P is the prior. Now note, in none of these cases I actually consider what's actually the state, so we'll need to also include that. That's going to be a big factor. Let's just do it. Self.s is equal to state state at which this action was taken. The state can be two things. Like yesterday, what we are trying to do is that the state could have been the board FEN string. But in our case, as I showed here, that we would like to keep the state as what was the board stack till then. I'll explain what the board stack is. So you have n is equal to 1, you have the q, and you have the state. Okay. We should probably improve the REPR. Self.move value. So what is this particular value? The value is, so this value is if I took this move, if I'm at this particular state, which is A to A0, what this value is, if I take the move A9, what is the value I get now? Value is equal to mount this. Okay. So this actually is the Q value. As you can see, theoretically this is our Q value, because we don't have, there is no difference between what a state is and what an action is, because the entire thing right now is that we only are giving it actions. It's supposed to have an internal representation of that state. Oh yeah. So that cleans this up. This is done. This value is actually the action value, and let's just write a little bit of talk saying what that is. So you have all these moves that have been taken, right? And so the value is actually what the model says happens if all these moves exist, and I also add a move a9 which is equal to q of SA. Is that right? But I'm so stupid. So I've taken all these moves and I take a particular action. Now these are not the same things. This is the value of that state. What happens to the entire game? What would be the result of the entire game if I take this particular action in this particular state? This is not let's just say this is, assume I am right. That's not usually true, but okay, let's just consider this right now. So I don't need this queue, and now what we need to do is we need to include the states in this particular function. Now when I'm initializing the node, which is here, and here, okay, so my value is this, my move is this, my probability is this, and also I need the state S is equal to b dot move stack. Okay, my argument is can't set attribute. What does that even mean? What is this? Can't set attributes. Name doubles are immutable. Oh, not this, man, not this. What is happening right now? I need a setter function. Oh my god, no. This is not C++. We don't have that in Python. Come on, man. Okay. Can I do this instead? I can give it the board. I can simply pass it the board. What I'm going to tell is that you need to go to this. What does that even mean? Can't set attribute. Passing a list. Okay, so it takes in the board. Okay, so it does take in the board. What if I sent it this thing? Okay, so it takes in this. I can't use self.s apparently. Okay. Okay, perfect. So this thing, what I need to improve this particular string, which is what we're going to do is children occurs n times. It has len state. This is basically moves. We're not going to use this thing anyway. Let's see, 3 moves. Okay, perfect, it makes sense. What it's saying is that no, I need a better string, which is, we're going to say this is C, and we're going to mention this as n is equal to, and C equal to is this. Let's see. And then we can say S is equal to this. See, so much better. Okay, this is each of our nodes. Now when we're going to actually initialize this, we need to pass it all these things, which is the state, p, move, and values. We do that here, and so we are going to add this here. Value is this, move is equal to this, p equals to this, and the last thing we need is state equals, I can actually just do this. I can pass it the board, and I'll just tell it that, just extract that board from here. Just call it B. So B is equal to B. Okay, perfect. So your B, where's this? B is equal to B copy, B future. Alright, I hope so. Okay, so total nodes is equal to 111, and it has done this. But the reason it's saying that these two things are same, if this, so what we need to do is we also need to define is it actually ever in the same state. Should we go over the internet and start looking at the code for Monte Carlo tree search? We can, but that would be cheating, and we should not do cheating. It's a bad thing. Okay, let's read what's happening here. This contains edge SA for all legal actions A in S. Each edge stores set of statistics, probability, prior probability, W and BR are the Monte Carlo estimates of total action value accumulated over NV and NR leaf evaluations and rollout respectively, and QS is the combined mean action value for that edge. Now at each time step t less than L, an action is selected according to statistics blah 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 using the variant of PSCT evaluation. But won't the state actually change? I mean, if you're here, you take this particular move, the state, even after So you take this particular move, which is putting the that black thing here, black unit. I don't know. You put the black piece here. Now, even if you come back, if you take the same action, which is putting the black piece here, it can never be when you do the same state. It might be possible that if you take this particular action and you realize that after a lot of moves, it comes back here, the states are actually not going to be the same. So what I think this means is still that the state at the starting should actually be same, or the other way to think is no two state. If it's a board game and both the players are actually taking moves, the two states can actually never be same. Okay, so apparently I'm too stupid to understand this, but let's see where it goes. So I'm going to assume that the states are actually same, because it's not possible to act. No two states can ever be the same. So how would the Monte Carlo search actually work? I'm not exactly sure about that. So I'm going to skip that piece for now. Let's just go ahead with it. Now we know that this value, again, an assumption that this value is actually the action value because of the way that we have structured our problem and the model. The model does not predict what is the value in that state. It actually takes in all the actions, it puts in the next move, which is the next action, and again predicts some particular value, which it automatically, because of its formulation, is predicting the QSA. Now the QSA is actually given by this. So let's see what would be the greedy search what would be the searching algorithm here. Okay, so let's start writing this. It's basically going to be a minimax. What we need to determine is in this particular state action A, def best action for this root node. If I've been given a state like this, what is the best action that I can actually take? So for that, what I need is two values. One is the QSA. So Q is basically the root node dot value, and we need the second piece, which is pretty big, but let's just start with it, which is it's a constant. So constant is actually 1.25 plus np.log, and this is going to be 19652. This is again going to be, so we can actually just write it as 1 plus some value divided by 19652. This value is actually 1 plus, okay, so we need this particular issue. We need what are all the moves that were taken in this state. Sum of all the moves that was taken in this state. For this, I don't need to store what were all the possible moves. What I need to store is self-dot all possible actions, which actually is, if I just take this particular board stack, I just need to see what are all the legal moves. So NSP is equal to sum 1 for this in xb dot legal moves. सर्दी हो गई यार. And यहाँ पे NSP लिखा. Sometimes I think like Hindi is so much more easier to talk in, but let's be. Self.nsp is this. Does it work? NSP is 21. right? So does this NSP, I have all these NSPs, I do this, and just to check, we can also do a print root node, and let's see what happens. Yeah, so it's saying that all the possible sum of all the possible moves in this particular state is 21. So that 20, so this particular game has like a pretty big branching factor, branching factor 21, 21, 22. The average branching factor for the game of chess is actually 13. Average branching factor chess. Yeah, average is said to be 35. Alright, he's mean on an average a player has about 31 to 35 legal moves. So I was wrong. I thought it was 13. Well, that means it's pretty tight, which means that it's not playing all the possible legal moves that it has. Oh, sorry, yeah, whatever, you got it. Okay, so this, and now all we have to do is we need to do a root node. This is not exactly a root node, this is any given node. We need to calculate this. So any given node is actually going to be dot nsp, and this thing is multiplied by np.sqrt divided by 1 plus node.n, yes, np.security node.nsp. so this is a constant, yeah, 1.25 plus this is this into this is this. Where are these coming from mu0 paper. C1 is equal to 19625, and this is C2, and C1 is equal to 1.25. okay, now the constant, and now the adjusted UCB value is actually Q, or let's just call it node dot value. We don't need too many lines of code. I have this policy that if I have to write more than 50 lines of code for any one thing that I'm trying to do, it's not a good code, and usually this thing has served me pretty well. Const, and so the action is going to be argmax over all the possible actions. So what this does is, let's just call this function UCB val, and this returns this particular value. So if I give this thing the root node, it should tell me something about it. Okay, say let's just see, root node has this thing, and if I just print root node actually has the value of minus 0.55. right now root node has the value, okay, n is equal to 1, which is why it's not giving the correct value. Okay, so we haven't actually updated what happens here. How do we do that? Okay, for C and AC, which is all children, here we have an AC, right? Okay, for C and AC and all children, C dot n is equal to cntr C dot move. Alright, if I do this root node dot children 0 or 9th, yeah, whatever. is the n actually being updated? Print C, print C. Okay. Okay. So it's not exactly updating these things. Do we add this function here? Update n for children. How would it do it? It has to be recursively, so it has to be here. All the recursion things I've added here because I'm pretty bad at this thing. Def update n. Self. Nah, man. Nah, it's too complicated. So it does get actually updated. Oh, because this thing comes 1, that's why it's not turning the correct value. Makes sense. So I can do, just to check, I can actually do this. Children 0 dot children, and so we take 0 and this thing has it here, and we can actually calculate what was the difference in the values that this thing has made. So this was minus 0.63, which means that it was thinking that this is a pretty bad move. It's still a pretty horrible move, but at least it's correct now. Now if I just force it to update something like this, that this move has actually come approximately 100 exactly 100 times in my simulation, then what happens? Okay, what about 1,000 times? Okay, so 1 plus n, which means, because this thing because this is an upper confidence bound, what that means is that it actually favors, it starts off by favoring those moves which have only been taken once, right? So if I do this, you'll see a little bit of difference. I see, not that much, but still, give or take, people. That's life. Should we also add prior? Yeah, we should add prior. So let's just standardize this thing. V0, V means this thing. Move this. These are the values, and then we also need to include the prior, which is equal to. And this is a pretty long code. Self.b up to 3 floating points. That's it. So the play again, man, play again. Might play again, mate. So let's just do for our reference, we're actually going to do this. Cross 100 multiply by 100. God damn it. I'm just being a little, am I too stupid to do this shit? Maybe. Maybe, Barry. Maybe. How many of you actually watch Archer? Archer is a pretty decent show, man. Everybody should watch Archer. Okay. Okay, so the values have changed. So what it's saying is that the values that you're assuming are too bad are not that bad. Again, because these are still minus 0.11, it's still... Oh my god, I'm sleepy. Okay. So we have this piece done. Now, how do I take the best action? Def best action in this root node. What that means is that I need to go over first I need to now so I need to go over all the children and start adding this particular value in those children. Should I just call an update function? Update, yeah, that makes much more sense because all the values are already here. So what I need to do is def update q self. It's going to do the same thing, but because it's doing it internally, what that means is I don't need to deal with any shit. That's what it means. Self.q. Let's just call it let's just let be value, and we need to also set a flag which is self.update is equal to false. We don't want to have a bug where we keep on updating the q value where because then it's stupid. If self.update if self.update raise value is stupid, man. Assert self.update is false because value already updated. Calling multiple times can cause an issue. Okay. So now because it's taking all these values internally, the node becomes self and that's it. Now I don't need an external loop to actually run this thing. How do you change it? Because no, it doesn't really matter, because when I'm actually searching, all I need is to take the best action. I don't need anything else. It does not depend on what happens next, because right now I'm just doing a selection. Am I right? Or what is stupid? There's another thing that is included here that I have not done is that in my case I do not consider. We'll fix this. We'll fix this first thing. So all these algorithms, they also what they do is that after running through multiple states, let's just say Sn, it also predicts that this particular state is actually terminal. Alright, so these algorithms are run till they reach the terminal state using the fast policy ppi. Track the mean of all evaluations r and weight theta in the subtree below us. Let's just read this again. Each simulation traverses the tree by selecting an edge with a maximum action value q, a bonus up that depends on the stored prior probability for that edge. Again, because in our case the node is the edge. In our case, node does behave like an edge. Okay, the leaf node may be expanded. The new node is processed once by the policy p row, which outputs the probability stored as per the prior probabilities for action E. At the end of each simulation, so this is this piece. The leaf node may be expanded. The new node is processed. The leaf node may be expanded. The new node is processed once by policy p row, and the output probabilities are stored as prior probabilities p for each case. Evaluation. At the end of each simulation, the leaf node is evaluated in two ways, using the value network v theta and by running the rollout to the end of the game with a fast policy rollout p pi. Then hello, एक minute. Yeah, sorry about that. Okay, so each the leaf node is evaluated in two ways, using the value network v theta and by running the rollout to the end of the game with the fast policy p pi, then computing the winner with function r. Okay, the action values q are updated to track the mean value of all evaluations r and v theta in the subtree below that action. The leaf node may be expanded. The new node is processed once by the probability p row, and the output probabilities are stored as the prior probabilities p for each. So I didn't see anything like this in the mu0 paper. So you can actually search if it does it actually search anything. Cool. I didn't see anything like a fast policy. Yeah, I didn't see anything like that. What that means is that these guys actually evaluate using the same policy that they use for iterations. Policy p pi, policy p pi. So this is what they do. Yeah, so we won't be doing this. In our case, we'll actually be using the same policy for all these things. We have just one model. That's it. We're not going to do any fancy shit. Okay. What that means is you still use the greedy search and minimax search. Is that so? Because the value is already updated. So at the end of each run, what I need to do is okay. So let's start porting this code back into the repo. So you have this thing. The node is now completely updated. You have much better description for what shit is happening. And if someone comes up to me and says shit like, why don't you use the camel nomenclature or the PP8 nomenclature? No, dude, no, nobody does that. It's a horrible thing to do. It's pretty useless. So this was one main difference I had, was that I was actually zipping through all these arrays. Okay. So now what I have to do is, I was trying to actually add tree search with upper confidence bound, but that is actually not needed, because all now we have to do is, once we have the generate tree, all it says is, root node dot update of queue. Update queue. Okay. What update queue will do is that it should go over all the children for child in self.children. Okay. Child dot update queue. Cool. So what it's going to do, it's going to go over all the children. So the first thing it's going to do is, it's going to go to the leaves. It's at the leaves, it's going to update those values, and then it's going to update the values for all those functions, all those nodes that are above it. Yeah, okay. So this does that, and let's run one game, see what happens. Python 3 game.py. What we're going to do is minimax to depth 2. Is that still a good choice? You know what? Sorted minimax. You know what? Let's just run this thing. Let's see what happens. Okay. Init missing 2 positional arguments. Right. We did not initialize anything here. Root node gets initialized here. Value move. And along with value and move, we now have the probability of this move as well as the B. So we do not, having B is easy, it's B. The probability with which we are going to take this action is, how do you define it? What was the probability of taking this action? Is now what we need to do is okay, so we need to store with what probability which this was taken, which is basically the confidence. And the way to do it is, we took this move, and what we need is, so this sorted moves, so let's just do it like this. Node last is equal to sorted moves minus 1 move node. Yeah, boy, that's what I'm talking about. That value, and this is just this thing. Move node dot move conf is now equal to move node dot p. So this is the probability with which this thing was taken. Now what we need to do, and the laptop is getting too hot. I don't know why. What's taking such a huge amount of memory or processing power? Oh, OBS and terminal. I don't know, man. What can I do about it? CPU is at 11.1%, 10.9%. Recording is happening at 30 FPS. You know what? Fukit. Okay. Confidence. Now what we need is, root node is the value and the last move but what was the probability with which what this move was taken? I don't have a probability with what that move was taken, but I do need it. So these guys must be storing it because they do use it here, appendix B, right? So they do have uh, the problem is simple. Problem is that I do not know by what probability this move was taken, because the person who took this move was a different person. It was a different player who took this move. You know what? If we just start off with S, what it's going to do is that it's going to give it a 0 probability, but which is it's okay because I don't need to do anything with the root node. Oh man, where is it? Game.py. So the P can actually be 0 because it does not matter. I don't actually use that move. Let's see. None type object is not iterable. Where am I getting none type object? It's under tree process. Oh my god. Oh my god. Does not actually have the probabilities. Let's just add another assert here, which is that if this thing is none, then mv props is equal to np.array np.once len mvids divide by len mvids. Let's just give them a uniform probability of each of them taking this thing. Also provide probability as well. This does not happen here. I'm actually not providing it any probabilities. This is incorrect. Where is it? Yeah. You know what? Let's just add it. Root node. Every probability is going to be equals. I do not have any bias. Man, that's so stupid. Should have a bias. Tuple has no attribute or value. Okay, so move node is actually the 0 of this thing. So in this game, the black is the minimax wala thing, and it's playing. It's pretty confident that it's going to lose. So stupid. Oh God, it's not going to do anything, man. You know what it's actually going to do is that it's going to actually again just shuffle around. Sorry for the loud noise, people. Can't do much about it. Saying G1 F1, and this is also G1. So this is G2 F1, and this is G1 F1, which means this is somewhat like G1 G2 F1. Oh my God. G2 F1, and this thing got G1 F1. Whatever it was, actually moved one step ahead. How is it that both of them are confident that both are going to lose the game? And that's so stupid. You know what? Let's end this game. Let's end its life. Okay. Oh, dude, you're done. Okay, now what we're going to do is we're going to go and analyze how it was playing. Oh my god, I'm so embarrassed because these players are complete shit. Wait a minute. This did not save it. No. Supposed to save it. Let's just call it print saving. Man, wasting my time, man. So let's play around. We'll figure out what else can we do in our code. What are the other improvements that we can actually make? So one thing that we have done is that we have added a very stupid search algorithm till now, and we're going to continue with that only. Okay. So it has these probabilities. Now the problem we can see, one thing is that this particular algorithm is taking moves with very low probability. I don't know why that is happening, whereas this thing is taking moves with a very high and certain probability. There's definitely a bug here somewhere, or we are doing a mistake, more likely. How can both of them be sure that they are actually going to lose? You know what? Oh my god, this is what it is doing. It's not going to work again. I need to let it just run. You know what though? You know what? You know what? You're done. You're done, mate. You're done. And then we'll let it play for 25 moves, and then we'll just crush them. We'll tell it to stop. Alright, let's play. You know what, even if this is a bad search algorithm, it's fine. What we now need to do is we need to improve this function, because what it is doing, let's tap. Okay, macOS OBS. Oh my god, it's actually running at full power. Memory is okay, so it's not a very big deal. I mean, this thing is these models are actually consuming insane amount of power while they actually process like just 147 nodes. This is not a good thing. This is a horrible thing. They shouldn't be doing this. They need to be better than this. Come on, man. You're better than this. The one thing that we're actually doing stupid that we should have fixed is that we should have given it a probability value with what probability that it wants to take this move. So let's just add it here. P is equal to none. No, P is equal to 0.98. This is the probability that we are going to use for the top P nuclear sampling. Yeah, so P is equal to P, this, and is it done? Okay, this is done. Now let's go about and see. So the results, both of them are sure that they're going to lose. It's so stupid, mate, you're stupid. let's say, so here, it's this thing, man. See, the black is playing so stupidly, man. Why even trying to play? Playing a horrible game here. In fact, the model that works, that does the simple sampling, actually is playing much better, which means that it's actually taking those value. If it takes these values, um, now there's another issue. As you can see that the white is playing all these moves with much higher surety, whereas the black is not, because clearly we're doing something wrong. But what the probability that we have defined is actually the p-value of that particular function. So find the laptops slowing down. Hopefully it will go quiet. Ah, cool. I'm pretty. I was worried about another thing that I'm very happy that this is not doing, is that there's no memory leaks here. Those are the worst to fix. Let's just at least add these things. Git add this, git commit, add mct, no, add mu0 value updates, add mu0 value updates to node. Yeah, cool. Where will this project go? Is it actually going to work out? Well, if it doesn't work out, there are 1,000 other things I can do. At least one has to work. So when it was, what you're saying is that this is actually correct. What I need to tell it is the confidence with which this move was taken is actually the p-value of it. So that means it was updated here. So when it takes that one particular step, this is the confidence with which it was taken. Is it actually correct? I don't know. Okay. You know what? Let's take a break for 2 minutes. I'm going to listen to music. I'll mute this thing till then. I don't want to get copyright shit in my first or second video. This guy is a goddamn lyrical genius, man. I'll just MF2 lyrics. What does our Reddit say? Best MC with no chain you ever heard. That's true. That's true. Just remember all caps when you spell the man name. Oh. Bishop Nehru? Some guy with the name of Bishop Nehru? Damn. Kaitranada. Kaitranada. Catch a throat full from the vocal ash and the most like yeah. Just like to what's your hand? I need Santac. Arcane thank for blank into an epileptic shot. 2 minus oh my aching hands from racking in grants and breaking in the mic stands. Doom man, Doom. He's the guy. And Mad Villainy, single-handedly the best album ever made. Mad Villainy is a highly praised hip-hop duo of producers and MCs MF Doom and Madlib, signed under Stone Throw Records. According to the Pitchfork article, the two met after the then manager blah 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 blah. It's true, man, that's true. Okay, let's come back to this thing. The rollout policy (PPI) is a linear softmax policy based on fast incremental computer loop pattern. Yeah, okay, so it's a different thing. Rollouts execute approximately 1000 simulations per second per CPU thread on an empty board. Whereas in our case, we're able to get like 147 in 2.75 seconds. Now, of course, there's differences that these guys use Lua. When they're coding, there must be certain advantages of using Lua as well. There has to be something that we could have done better. Oh my god, are you kidding me? Training took around 3 weeks on 50 GPUs using test belief gradients older than 100 steps were discarded. Oh my god, this is too much, man. That's 5 million. Yeah, I was right about it. It's a little bit more than 1%, 10%. I have 29.4 million moves, and yeah, the first million positions, which means sorry, it was even less than this is 0.33% of your data set was actually used. Am I correct? Yeah, I'm correct. So, yeah, this makes sense. Hmm. And they really do go all the way in this thing, no? I need to read the Alpha Zero paper. The internet is so horrible. I'll just add it to my I don't have Brave. Where's my Brave? Yeah, let download this. Difference is that these guys are much smarter than I am. They have a goddamn team working on it. And secondly, they use the whole board, which makes sense with using conventional terms. Okay. So this is it. Alpha Zero was trained on 700,000 mini batches. It took 9 hours, and it was basically 844 million games, and thinking time was about 800 simulations or 40 milliseconds. Okay. So in chess, as you can see, they have like 73 different planes. This includes other planes as well, which they have not shown, which is the which player is playing right now, things like that. So if it's white, it's basically one complete layer of white. If it's black, it's complete one zero layer of black, for black. Okay. MCTS and alpha beta search. So if you're running 800 simulations and you're using a depth first Monte Carlo search, this is what these guys are doing. So I think we should try to implement that, because right now what's happening is that it's only going to one depth and returning that one particular value. For that we'll need to improve this particular location. And let's make this generic function. def they're also calculating the tree basically. If I had one entire if I had a gigantic tree that basically was storing all the possible trajectories that these games are going to take, then it makes sense that I would be able to use the priors much more effectively. But it's called one step. So let's call this move one future. This is going to take in all these values, and it's going to take in whether it is verbose, and what it is going to do is it's also going to take in the vocab and the inverse vocab. Verbose by default is going to be false, and what it is going to do is it's going to do this entire process. If verbose, and I also have the node. Yes. No, I don't have the node. What this thing is going to do is it's going to return three things. Return the future legal, return the this thing, and also return this node. And so what you're going to do here, we're going to copy this thing, we're going to bring it down to we're going to bring it down here, which is this place. What to say is this and node. One future, one life. Oh, I also need to take in the board. Horrible. This is what's taking the board, and board goes here, and bam, you have everything. Now what you do is you take this, you add it here, take this, paste it here, take this, you paste it here. Make one step in the future and return best values. Okay. So you can see what's happening here. The one difference that this thing is making is that we are still using a softmax probability. Oh my god, this thing is heating up again. You know what? Let's just close tab 9. I've been using this. This thing is actually very good. How do I stop tab 9? This thing is insane, man. This thing requires an insane amount of battery. I think this is one of the primary reasons why it's taking it's heating up so much. Right. So what we have done till now is that we have still told it that these are all. So we are still searching over this probability. What this means is that it's still going to return a very deep searching method. What I mean by that is that p is equal to 0.98, and what I need to do is I need to include p equals to p and verbose equals verbose. That makes sense. Okay, and this thing goes here. Now this search, as you can see, this search is actually using the a probabilistic method, which means that it's going to return a lot of it's a breadth kind. It has a very big breadth, whereas what this algorithm does is that it simply takes in what was the q value and the p value, and boom, it returns that thing. So we'll improve the selection now. Let's just copy paste this code into a Jupyter, make things consistent. Not generate tree, all the way above this thing. Cool. One future, one life, one step, one future nucleus sample. So we should have mentioned this thing. Let's just mention this thing here for now. Okay, so the one thing that we're actually trying to do is we can say expansion the way that these guys are doing, which is they simply take the they do the selection by taking the first no, each selection traverses the tree by selecting the edge with the maximum action value q plus the bonus pq. The leaf node may be expanded. The new node is processed once the policy. Okay, so the policy networks, it basically returns with what I am able to understand is that the policy network basically returns the probability of which possible actions are to be taken, right? So if I'm here, it takes this particular thing and then it says that these are all the probabilities. I calculate the q values using those updated q values using those probabilities, and then simply what I'm going to do is I'm going to select the best action. Then how is it a upper confidence bound? It would always select it would always select the probability that has the highest value. But let's just see how it goes. So I have a node. I get these following things, which is the move. Now, one step is too engrossed in that particular thing. We need a better way. Okay. So we will make a new function here, which is one step expansion. What that is going to take in is that it's going to take in the model, of course. Damn it. It's going to take in the model. It's going to take in the node, the B board. It's going to take in what is the current node, not exactly the root node, but let's just call it the root node, because it's going to be the root node for this particular factum. You have the vocab, you have the inverse vocab, which is used for debugging, and you're going to have not the move IDs to take. No, you do not need those move IDs. Neither do you need the move probabilities. Till this point, I know what action has to be taken, or what actions have been taken. So now all I need to calculate is, of course, verbose is equal to false, and I don't have any p. So what that means is I know what action has to be taken. Move to take is going to be, let's just have move IDs. Well, I already have the move IDs. Move patched. Yeah, this is what I mean. This is what I mean. So I have the game start flag, and then I have a move stack, and then I don't need to go over all these nodes. So what I need to do is, I've been given this kind of a move stack, and I don't have the move IDs. I just need to, because I need to take that move which is taken, which it's done using this kind of an approach. So I'm going to say that I have all the moves that have been taken till now. I'm going to go over this thing. I'm going to pass it to the model. Okay. Now this model is going to tell me what are the best possible. It's basically this piece. Now we do the expansion. Note, please note that we have not actually done the selection till now. We are assuming that till now the selection is already done. Assuming that the selection is already completed. Do I need like typing classes or something? Selection is already completed. The expansion, the way that we are going to actually expand this is we have all these possible logics that we can do. It tells me what moves do I have to take in the future. I'm not going to do that. What I need to do is I need to find all the legal moves that can be taken for this particular board. So what that means is I need to calculate this piece. On this board till now, what are all the legal moves I can take, and then I need to filter out logits. Is basically I don't need all the logits. See, logits right now it's a one batch thing, so I can just do this, and I can do legal. I do this, and then I do a simple softmax. Ain't that right? Yes, I do a simple softmax. These are all the possible moves that can be taken, and what I have to do now is I'm going to add all these nodes. I don't need to use the update formula here to actually determine what particular value should be taken. I can simply calculate it right here. So what I'm going to say is that self.nsp is actually the length of all the legal moves that it's doing till now. And the number of times that this thing has visited here. You know what I'm going to do? I need to go to the bank right now. So I'll just end the stream here. I'll figure out how to implement this thing off stream, and once I've done that, I'll tomorrow I can start the stream again in the evening. So I'll just at that point of time I'll actually just start streaming again and add it. Okay, so let me just show my face so we can be done with this thing. Thank you for watching. Do I have to say this? Share, like, subscribe, and okay, I'll see you next time.